My name is Samir Khan, and I'm a product manager at MapleSoft. At MapleSoft, we've been developing mathematical software for a long time, perhaps decades. So we've learned a lot about the entire market, everything from the little details to the bigger picture. Personally, I've been knee-deep in engineering math for my whole career. That's either in consultancy, training, technical support, or product management, my current role. I'm also the type of geek who likes playing about with math software as a hobby, so this is something I'm deeply invested in. Math and engineering math are a little different. The former has a certain intellectual purity about it, while the latter exists within a broader context that's influenced by the needs and requirements of industry and engineers. This presentation is the first of three. The second two will be deeper dives into electrical and civil engineering calculations. In this presentation, however, we're going to explore the properties and requirements of engineering math and what is required from engineering math. And when I say properties, I don't just mean the provenance of the individual equations. I'm talking about the whole life cycle, from their derivation using the laws of pure math and physics to their implementation in software and how they're presented and managed. We'll also reference the primary stakeholders in engineering math, engineers, and the organizations that employ them. If you're an engineer watching this, you might gain some perspective that'll help you enjoy calculations more or make better tool choices. If you actually manage or influence a group of engineers, then you might gain some perspective on how you can treat calculations as a valuable, vital company asset. And I'm going to start by asking a question. What differentiates an engineered product from a crafted product? It doesn't matter if you're a civil engineer designing a bridge, an electrical engineer doing circuit analysis, or a petroleum engineer designing a distillation column. The answer is always the same. The difference between an engineered product and a crafted product are calculations based upon the fundamental principles of mathematics and science. Now, you might think of math as something you had to grin and bear during your time at university, or you might be a geek that enjoys math and playing about with technical software. Whatever perspective you have, you've got to agree that calculations deserve at least a modicum of care and attention. Now, to give engineering calculations their due respect, we need to understand and appreciate their properties and requirements. These stem from three sources: the provenance of the equations from the math and the physics, and how they should be presented to maximally convey meaning; the engineer that does the calculations, their perspective, and how ideally they want to interact with math software; and the organization that employs the engineer to do the calculations. We'll talk about each of these in greater detail. But let's start off by discussing the math, its properties, and the presentation of calculations. There's a summary of the key points here, but we'll talk about these in greater depth. Let's start off with this. So how do we get the equations in your engineering textbooks? Well, they're derived from a combination of physical laws and mathematical identities. The mathematical identities could be something as simple as the area of a circle or a calculus identity, but the physical laws could be a heat and mass balance or some application of thermodynamics. It could be from the conservation of mass or momentum, or it could be Kirchhoff's current and voltage laws. Generally, you need to go to university to learn about these concepts. But when you work professionally, unless you're on the research side, if you do math, you might not do any direct derivation of equations at all. If you are deriving equations from first principles physics, then you're either doing this by hand, or if the system is complex enough, you're using software. You might be using computer algebra tools. Now, a lot of the time, some very clever people have already done the heavy lifting and have used these physical laws and mathematical identities to model complete systems and validate those models against field data. These calculations could govern the design of concrete retaining walls, or the safe working distance to prevent an electrical arc flash, or the thickness of a pressure vessel. Somebody's already done the derivation of the equations. Somebody's already validated those models, those equations against field data. Now, the results are available in design guides such as the International Building Code or the IEEE design standards. And many engineers simply take these standardized approaches and apply them to new situations, new applications. Now, engineering equations, and specifically the parameters in those equations, are inherently dimensional. The lengths, the forces, the voltages, the masses, energies all have dimensions, and the dimensions matter. You have to get them right. In fact, the dimension is as much of a part of a parameter as is its numerical value and should be carried along with it. In a spreadsheet, the required unit might be specified in a text comment by the number, and it's up to the user to do the unit conversion. In other calculation tools, the unit might be a part of the parameter definition or the metadata of the parameter definition. We've all heard stories about what happens when you get the units wrong, and you might have made one of these mistakes yourself as well. One of the most spectacular instances was the Mars Climate Orbiter disaster in 1999. The disaster resulted from a navigational error. Commands from Earth were actually being sent in English units, while the orbiter expected those same results in metric units. And there's a big difference between pounds for seconds and Newton seconds. The orbiter fell into an orbit around Mars at about an altitude of 35 miles, which is far too low, and it simply disintegrated due to atmospheric stresses. There were actually rocket scientists working on that, working on the calculations, on the programming code, but you simply don't need to be a rocket scientist to make errors with units. Anyone using a spreadsheet can make a unit conversion or a consistency error. Now, in my time in technical support and training, I've seen lots of engineering spreadsheets with lots of errors. Many of those errors result from dimensions, unit conversions. Of course, Excel doesn't understand dimensions. It doesn't perform unit conversions, and it certainly doesn't put any checks on the dimensional consistency of equations. That's left up to the user, and anytime you do that, anytime you don't automate or mechanize via software, you just leave the door wide open for expensive errors. The way equations are presented carries context and that meaning, and that context is important. Let's just say that you see this number divorced of any meaning or context, either written down on a piece of paper or in a spreadsheet. You could ask yourself, what does this number represent? What does it mean? How is it calculated or generated? And quite often, this number is all we see in a spreadsheet unless you drill down into the cell and decipher the equation. There might be a few context clues in the form of text, comments, or the title of the spreadsheet, but invariably there will be some detective work involved. So, how would you need to see this number presented in order to give it meaning? Here we have the same number given context, clarity, and meaning by making the equation explicit. You know that you're calculating the area of a circle. You could also infer that somebody measured this diameter with a pair of calipers, or they found the value in a table. The units are also explicit. So one of the benefits of using dedicated engineering math software is that the unit might be formatted differently from the other elements in the equation, perhaps with a different font or a color or a weight. So you know it's a unit as opposed to an assigned name or a built-in function. And that, I think, points to a broader question of how entire calculations should be presented to maximally convey meaning. There's the concept of the engineer's notebook, a bound pad of paper filled with equations and notes. And for this, I love to reference the calculation notebooks of a personal engineering icon of mine, Isambard Kingdom Brunel. He was a Victorian engineer who worked in the UK in the 1800s. He designed bridges, steamships, and railway stations with nothing but intellectual flair, diagrams he drew himself, and calculations he did by hand on paper in his notebooks. His original calculation notebooks are still preserved at the University of Bristol. The picture you're looking at is the Clifton Suspension Bridge in the UK. It was based on an original design by Brunel and opened in 1864. And on the right-hand side is a photo of a page of one of his calculation notebooks for this. When he needed to work out the length of the chain or the height of the connecting rods, he derived the appropriate equations for the shape of a catenary. That involves some calculus. He substituted in numerical values and approximated the results. So he used whatever tools were available at the time to do his number crunching, his calculations, but his paper notebooks were the center of his technical desktop. That's where he did his calculations, wrote down his notes, and drew his diagrams. His work is still eminently readable. It's still understandable. And in terms of presentation, I think this is still a standard that we should be aspiring to. Now, on the subject of paper notebooks, paper is still the most intuitive working environment of all. I work in a tech-heavy industry, software development, and people still take notes on paper. There's a certain tactile feedback that you get from paper and pen that's really difficult to reproduce electronically. So when you're doing an analysis, sometimes all you need are basic arithmetic operators, but often your analysis requires a little more mathematical grunt. And by that, I mean something you can't easily do in a spreadsheet. So you might need to numerically solve an algebraic equation. You might need to solve a differential equation or perform an FFT or do some data analysis. You might also need some plotting tools as well. You might need tools to visualize the frequency response of a transfer function. That requires computational support with software that gives you higher level functions than you get in a spreadsheet. We've now discussed the properties and requirements of engineering math from the perspective of the equations and calculations itself. To summarize, the equations are derived from physical laws and mathematical identities. The parameters are dimensional. The calculations should be presented in a clear, understandable form to maximally convey meaning. Sometimes you need computing horsepower for advanced mathematical support. And perhaps the design metaphor of a calculation notebook is the standard that we should be aspiring to. So let's move on to the human factor, the engineer. So without the engineer, you wouldn't solve any engineering problems. An engineer sits very firmly in the middle of the problem-solving process. Let's talk about how engineers traditionally solve math-based problems. Now, this is very subjective. This is very different from engineer to engineer. Some engineers are very, very methodical. Some engineers don't like math at all, but I think this holds true for most engineers. The way most engineers solve math-based problems is loosely structured. Some uncharitably would say haphazard. They know where they're heading, but they don't quite know how to get there or where to start because they don't have all of the computational steps planned out in mathematical detail. They progressively refine their analysis, correcting mistakes as they go along, or they go back a few steps to fix an assumption. So problem-solving tools, math tools, should be designed to get the best out of the engineer by supporting that very human-centered, loosely structured workflow. So people also have a very limited amount of short-term working memory. So if you're doing anything non-trivial, you need to make notes as you're working. Many engineers are actually apprehensive about doing calculations, but that doesn't necessarily mean that they're apprehensive about the math itself, but sometimes it's about the software that they're given to do that work. And of course, people get frustrated. That might be because of some ambiguity in a reference text or because of the mental overhead needed to use a math tool. You'll need to work through that to complete your task, but that stress, that frustration will make it less likely that you'll willingly do similar work in the future. And one underrated influence is that people like short-term gratification, and that's not necessarily a bad thing if that blast of feel-good neurochemicals is a reward for completing a discrete task and doing it well. And that brings me quite neatly to talk about a psychological concept known as the flow state. You might know it as being in the zone. There's a definition of the flow state from Wikipedia here. But briefly, the flow state is when you're so immersed in your present task that outside distractions simply melt away. You're concentrating and your problem-solving skills are firing on all four cylinders, and you just feel great, and you have a sense of accomplishment when you complete your task. I think developers of problem-solving tools for engineers should probably try harder to provide tools that positively encourage a flow state. And this is something that I'm very personally interested in working for MapleSoft. And here's what I think leads to good software user interface design to encourage that feel-good factor when you're solving a math problem. And if you're looking to adopt a math tool, I think that these agnostic guidelines are a pretty good rule for you to follow. The tool has to have simple game mechanics. That is, there are a reasonable number of syntactical and user interface rules you have to follow to use the product successfully. Not so many that you're completely overwhelmed, not too few that you don't have the flexibility that you need and your progress is impeded, but the right amounts. The interface should be simple. It should be designed with basic and intrusive style with as few distractions as possible. And there should be graphical hints to guide keyboard entry and mouse clicks. And the software needs to be responsive. It needs to be fast. Your actions have to have a quick response, whether you're clicking on something or trying to complete a computation. People simply don't like waiting. And you should also encourage a smooth travel of fingers across the keyboard and mouse. So if there's a common task, is it available via a simple keyboard shortcut, or do I have to take my hands off the keyboard and go to the mouse? If I'm using the mouse to drag things around or to click on things, do I need fine motor control to select and drag, or can I be more haphazard? Now, let's talk about the differences between different groups of engineers and their requirements, their perspective. Not all engineers are the same. There are many different ways of slicing and dicing the engineering community into recognizable, manageable groups. For example, you could look at the differences between civil engineers, electrical engineers, and chemical engineers. For calculation tools, one good way of managing the differences between different groups of engineers is to recognize the difference between research engineers and design engineers. Research engineers tend to have more in common with mathematicians and programmers than design engineers. They're the guys deriving equations from first principles physics, or the researching and developing algorithms to solve new and novel engineering problems. These guys are typically using software tools like Maple, MATLAB, Mathematica, or Python. They're more likely to work alone, and they generally only present the results of their analyses to the colleagues or management, not the whole thing. Then we have a broader swath of engineers who we can term design engineers, and their mathematical needs are rather more simple and prosaic. They're probably more interested in the application of math rather than math itself. Their equations or mathematical methods are probably already well established. They're actually on a well-trodden path. They just need software to click all the blocks together in the right order with the least cognitive overhead. They're more likely to work in a team and share the entire analyses with either colleagues or clients. And the tools for these guys tend to be spreadsheets like Excel, MathCAD, and MapleFlow. So I estimate that there are probably 10 times more design engineers than research engineers. So design engineering is a big market for calculation software. Of course, there is some overlap between the two groups, but by and large, for math software, this distinction is sensible. So we finished talking about engineers. Let's move on to engineering organizations and their intersection with math. So the goal of the organization is to ultimately build better products and services and create value for employees, investors, and customers. An engineer simply doesn't, an engineer just do the analysis, leans back with an air of intellectual satisfaction and then puts the result in a drawer. That has to be used to make an informed decision about a product design or a service. You have to do something useful with the results. And an organization needs to decide if they have the right tools for this. If an organization, a company, sticks with spreadsheets for engineering math, then they've implicitly agreed to whatever is good or bad about spreadsheets. The good is the ubiquity and the lower training costs. You can't underestimate the value of that. But the bad is the bottleneck on auditability, the ease with which you can make mistakes, and the lower ceiling on mathematical functionality. If a company has decided to invest in math tools or problem-solving tools for engineers, the upside is the gain in personal efficiency for the individual engineer and the greater process efficiency across the entire analysis group. Of course, that has to be balanced against the initial capital cost and training. Communicating that balance, the balance between the pros and the cons of making that investment in calculation software, has to be meaningful. And one method is to determine the return on investment in analysis tools. You can make this simple or complex. There are many different methods. Each differ in fidelity and the number of factors taken into account. So the costs are simple to estimate. If a vendor tells you that a software tool costs $2,000, then that's fixed. You could also take into account the cost of annual maintenance, training, and IT services, and that's not difficult to get an accurate number. The productivity gains from better math technology are a little more difficult to estimate, and you might only get reasonable estimates after you've actually used the software in anger for a year. And that's when you actually have field data on productivity gains. But you can still come up with some conservative numbers. If a company has decided to treat calculations as an asset, then there's probably been some thought given to how electronic calculations will be archived, shared, and secured. You need some kind of structure in order to bring sense to the system. That might just be a shared network folder with rules to follow about files, file names and subdirectory names, or it could be a complete PLM system if the organization is large enough to afford the licensing costs. If an engineer does leave, or there's some changing in staff, storing their analyses, their work in a structured, easily accessible forms means that the new guy, the new employee, doesn't have to reinvent the wheel. They can ramp up pretty quickly. They can carry on with the previous guy left off. So tool choice and documentation storage is even more critical in highly regulated industries like aerospace, defense, and nuclear power engineering. The lifetime of a project in any of these industries could be upwards of 20 years, 30 years, and any calculations and design decisions based upon those calculations have to be preserved for that length of time. In case of an accident or a remediation project, calculations have to be scrutinized to understand how the original design decisions were made. And that prompts the question, how should those calculations be preserved? Well, it's likely that PDFs will be readable for that length of time. There's a version of PDF based upon an ISO standard for long-term document storage and archival. And there's enough ubiquity with PDFs that I can see PDF readers being available for a long time. I also know of some companies who do the calculations on a computer. They generate electronic calculation worksheets, but then they print out their analyses on paper and store that paper in archival conditions for the length of that project. And as I said earlier, that could be 20 years, it could be 30 years. So if your organization does some or all of that, you're basically treating your calculations as an asset. If you invest in the right math technology for your company, that increases the engineer's personal productivity. You might also make them happier and satisfied because they have pleasurable tools to use. By storing your calculations in an easily accessible, easily retrievable, well-structured form, you can maintain a smooth continuity of knowledge across staffing changes, and that ultimately leads to greater process efficiency across the entire organization. So we've finished talking about what's required of calculations from the perspective of an organization. To summarize, calculations should be documented and in a form that's auditable. Calculations are a company asset. They're part of the IP that's created and should be valued as such. And in highly regulated industries, calculations have to be preserved for the length of a project. And that could be a long time, that could be a decade or more. So we're nearing the end of the first presentation. We've spoken about how engineering math is derived from physics and mathematical identities and how calculations should be presented to maximally convey meaning. We've spoken about engineers and different types of engineers, how they solve mathematical problems, and how software should be best designed to maximize their problem-solving effectiveness. We've also explored how engineering enterprises can make the best use of their math and the calculations that their engineers are doing and the IP that the engineers are creating. Now, you might ask why I and MapleSoft are specifically interested in all of this. Well, all of this influences, informs, and guides what we do, the tools that we develop, the interface to functionality, and even how we market and how we sell our tool and how we sell our tools. And I'd like to end with this slide. MapleSoft offer two calculation tools which are aligned and coordinated with the concepts that we've just discussed. Maple is a mathematically oriented tool for research engineers. It's the right tool to pick for mathematically intensive tasks if you're focused on the mathematics itself, or if you're developing an algorithm or creating an interactive application. MapleFlow, on the other hand, is a whiteboard-like scratchpad environment for math and documentation. It's aimed at the simple calculations and documentation that design engineers do. And in the remaining two presentations, we'll take a good run at what type of calculations electrical and civil engineers do, primarily in MapleFlow. But for now, thank you very much for listening, and I look forward to speaking to everyone in the remaining presentations. Thank you.